If you're listening to this, you're probably just as fascinated as we are by the constant evolution of machine learning and how it's pushing the boundaries of what we thought possible. I mean, today we're going to dive into a paper that's really changing how we think about something so fundamental, how AI interprets cities. Not just like looking at a static map, but really understanding how urban spaces function.
It's a huge shift because when you look at all the ways machine learning is tackling urban challenges, right? From traffic prediction to like optimizing emergency response, it's pretty amazing. But the way these models see a city, it often relies on these kind of rigid divisions, almost arbitrary, like sticking to official boundaries or just slapping a grid on top of everything. This new research is saying, hey, wait a minute, there's got to be a better way.
And the paper that's grabbed our attention is titled Boundary Prompting: Elastic Urban Region Representation via Graph-Based Spatial Tokenization. It's a mouthful, I know. But the title itself kind of gives away the game. It's all about overcoming those limitations of fixed boundaries and allowing AI to understand a city in a way that's much more flexible and adaptable to the specific problem you're trying to solve.
Yeah, adaptability is key here, especially for our listeners who are deep into this stuff. Think about it. You're trying to figure out the best spot for a new community center, right? Just using official city zones might not tell you the whole story. It might not capture those real social connections or the shared spaces that matter most to the people you're trying to serve. You need a way to define a region based on actual interaction, not just lines on a map.
And that's where this paper's framework comes in. It's called BPURF, the Boundary Prompting Urban Region Representation Framework. The big idea here is to represent a city not as a bunch of predefined areas, but as a set of tokens, kind of like building blocks. You've got things like restaurants, roads, parks, almost like the vocabulary of a city.
But these tokens aren't just floating around randomly. BPURF creates what they call a spatial token dictionary. Basically, it's a map of all these urban entities and how they relate to each other. Imagine a network. Each point of interest, each road, is a node. And the connections between them, proximity, what their functions are, how they relate, those are the links. This way, the model starts to see the city as this interconnected fabric.
Now, here's where things get really cool. BPURF also has this region token set representation model. This is the engine that can take any defined boundary. Doesn't matter what shape, doesn't matter how big. And it figures out exactly which of those individual tokens are inside. Then it learns to create this compact summary, like a numerical fingerprint. It's called an embedding. It's kind of like turning a complex urban area into a simple set of numbers that a computer can work with.
Exactly. So instead of just training on, say, a fixed set of neighborhoods, BPURF learns the fundamental building blocks of a city and how they connect. Then you give it a boundary prompt. Maybe it's a circle around a train station. Maybe you draw some weird shape on a map. Doesn't matter. BPURF can grab the right tokens inside that boundary and create a representation for that specific area, even if it's never seen that exact shape or location before.
It's powerful stuff. And the researchers highlight two key things that make this whole thing work. First, that detailed spatial token dictionary. Second, the model itself, which can take this collection of tokens from any boundary and generate a meaningful embedding. Plus, they've developed a super efficient way to find those relevant tokens for any given boundary. So really, it's all about breaking free from those rigid one-size-fits-all ways of understanding urban regions.
Yeah, let's dive into the paper itself. They start by explaining why this approach is so needed. In the introduction, they talk about how important good urban region representation is. I mean, for all sorts of crucial tasks, predicting crime, understanding where people are checking in on social media, even predicting population changes. All this is gold for urban planners and policymakers.
Right. And as they point out, the current models out there rely heavily on those fixed boundaries we talked about. Think about it. A lot of models are trained using like official city boundaries, like boroughs in a city, or just dividing the map into squares, like 1 kilometer by 1 kilometer. It's convenient, but it misses a lot of the real world nuance.
Right, totally. Like, imagine you're trying to figure out how walkable a neighborhood is. Those administrative lines, they rarely reflect how people actually experience the area. What's truly walkable often spills over those borders. So these current models, they're kind of forcing a square peg into a round hole. And you end up with these potentially inaccurate analyses of things like accessibility or, where resources are really needed.
And that's the big gap this paper's trying to bridge. So they introduce this concept of elastic urban region representation, or UUR. The idea is that you can define regions on the fly, even when the model is making predictions. And it can still create a meaningful representation, even if it never saw that exact region before. It's a big shift in how we think about urban data.
Right. And their solution. Boundary prompting. It's a really cool analogy to prompting in natural language processing. Just like you give a language model a prompt to guide its output, here you're giving it a spatial prompt, the boundary. That defines the region you want to understand.
And BPURF, this boundary prompting framework, is how they make it happen. It's built around that spatial token dictionary, the representation model, and that efficient token extraction. The researchers are really emphasizing a few key contributions here, identifying this overlooked issue of fixed boundaries, proposing BPURF, and then proving its effectiveness.
Getting into the nitty-gritty, they lay out some important definitions. An urban entity is anything with a location and attributes. Think of a restaurant. It's got its opening hours, customer reviews, all that. Or a road with its speed limit, its traffic volume. Then an urban region is just any area enclosed by a boundary. It contains a bunch of these entities.
And the really important definition is the elastic urban region representation problem itself. Basically, it's learning a function that can take any region within a city, any shape, any location, and turn it into a compact numerical representation, that embedding. This is different from traditional approaches where the regions are fixed, they're predetermined.
Yeah, they give this great example to illustrate the difference. They compare those standard government areas and grid cells in cities like New York and Jiangdu to, say, a 10-minute walk radius around a subway station, or a 15-minute drive time around a hospital. When you're looking at something like urban livability, it's clear that those fixed boundaries don't capture the functional areas of a city. Different questions need different ways of defining a region.
Makes sense. So how does BPURF actually do its thing? First, it builds that comprehensive spatial token dictionary. Think of it like taking inventory of everything important in the city. Then during training, it sees tons of random region boundaries.
For each of these regions, that super fast token set extraction kicks in. It identifies which tokens fall within the boundary. Those tokens together make up the region token set. And the heart of BPURF learns to turn these sets into those embeddings, those compact representations that capture the essence of each region.
Now, when you're actually using BPURF, say, predicting crime in a new area, you provide that specific boundary as the prompt. The same extraction process finds the right tokens, and the trained model creates an embedding for that region. It's like the model has learned the language of the city and can understand any sentence, any region you give it.
Now, building that token dictionary is foundational here. They transform every urban entity, every POI or road segment into a spatial token. Its attributes, like restaurant type or road speed limit, become virtual tokens. These tokens are the nodes in their graph. The relationships between them, like a restaurant being on a road, and between entities and their attributes, those are the edges. They capture how everything's connected. And they even use this technique called transar to get an initial embedding for each token based on the graph structure.
When it comes to representing a specific region, BPURF sees it as a set of these tokens, like a little subgraph. First, they combine the embeddings of all the tokens inside the boundary. They use a node encoder, which looks at a token and its neighbors to refine its embedding. Then, for each region, they do a sum aggregation per token type. So they sum up all the restaurant embeddings, then all the road embeddings, and so on. Finally, they combine those summed embeddings for each type.
And they have a strong rationale for using SU aggregation. They argue that it keeps both the overall region characteristics and the individual contributions of each entity type. Plus, it satisfies this mathematical property, distributivity, which helps ensure consistent predictions in later tasks. It's a clever way to capture the region's essence without losing the details of what's inside.
But aggregating tokens alone isn't enough, right? To understand how regions relate to each other, BPURF uses a multi-channel message passing model. This is where it learns how a region influences and is influenced by its surroundings.
Yeah, they have these different channels for passing messages between regions. One focuses on structural similarity. Do regions have similar types of entities in similar proportions? Another looks at their positions, how close are they geographically? And a third considers neighbor relationships, which regions are close by. Think of it like how neighborhoods affect each other, based on the businesses they have, how close they are, and their immediate neighbors.
And for each channel, they calculate an interaction weight between regions. For example, to measure structural similarity, they use dynamic time warping on the distribution of entity types. For positions, it's based on the distance between their centers. And for neighbors, it's just proximity that talk in closest regions.
These weights determine how much information regions share during message passing. The messages from all channels are combined to update each region's embedding, so it learns from regions that are similar, close by, or direct neighbors. This creates a richer, more contextual representation.
And to make it all efficient, especially with those arbitrary boundary prompts, they developed a fast token set extraction strategy. They use a spatial indexing technique, an R tree, to quickly find the spatial tokens, the physical entities, inside a polygon boundary. Then, they use pre-computed mappings to grab the virtual tokens, the attributes.
This two-pronged approach, spatial indexing for location, hash map indexing for attributes, makes token extraction super fast, even for complex shapes.
Now, in their experiments, they really put BPURF to the test. They used datasets from New York City, Chicago, and Shenzhen, covering tasks like crime forecasting, check-in prediction, population density, and traffic accident prediction. They standardized the data for those dynamic regions to ensure a fair comparison with existing methods.
They compared BPURF against a bunch of established models, general graph embedding techniques like TransR and Node2Vec, as well as urban region embedding methods like HREP and GRPP. They used metrics like mean absolute error, root mean squared error, and R squared.
And the results on those dynamic region prediction tasks are impressive. BPURF consistently outperformed everything else. Those other techniques, designed for fixed regions, really struggled with these new dynamically defined areas. BPURF showed big improvements, proving the power of its flexibility.
What's interesting is that they also tested a slightly more efficient version, BPURF Mini, which uses pre-sampled regions during training. It still performed well, but the full BPURF, which dynamically samples regions, did even better. This suggests that seeing more diverse spatial features during training is a big plus.
And it wasn't just about those dynamic tasks. BPURF also did really well on traditional tasks with fixed regions, sometimes even beating the best methods out there. So it's not just good at flexibility, it's a strong overall model for learning urban representations.
The paper also looks at BPURF's scalability and efficiency. That fast token set extraction resulted in a huge speed up, 1 to 1.5 orders of magnitude faster. Plus, performance remains stable across regions of different sizes, showing its robustness.
Finally, they did a thorough ablation study. Basically, they removed or changed parts of BPURF to see the impact. This confirmed the effectiveness of their choices for node encoding and the SUM aggregation. They also showed the importance of the message passing and each interaction channel, as well as the mobility reconstruction loss they used. Taking away any of these hurt performance.
To put this in context, let's step back and think about how spatial data analysis has evolved. Before deep learning, GIS relied on manually defined features and static boundaries. Early attempts at applying machine learning to urban problems were limited by the available datasets, which usually define regions in these fixed ways.
This paper is a significant step toward more flexible and realistic models of our cities. It's part of this broader trend in machine learning, moving away from rigid structures toward more adaptable and context-aware representations.
The key takeaway here is that BPURF provides a new way for models to understand urban regions. It breaks free from those arbitrary lines and grids. This gives us urban representations that are much more relevant and adaptable to the task at hand, leading to more accurate and insightful analysis.
Think about the real-world implications. Imagine analyzing access to services based on actual travel times, or understanding community boundaries as they're lived, not just officially defined.
Resource allocation could be much more efficient. Define areas of need based on real-time data and flexible boundaries that reflect actual demand. Policy development could be transformed. Evaluate interventions on dynamically defined communities for more targeted solutions.
And commercially, this kind of understanding opens up new possibilities. Location-based services could adapt to user-defined areas. Market analysis could become more nuanced by identifying natural urban clusters.
Now, in our Novel Notions segment, we like to explore potential future directions. Building on BPURF's boundary prompting, one interesting area is incorporating human language descriptions as prompts.
Oh, that's really interesting. So instead of a geometric shape, you could prompt the model with something like the busy commercial area around the main train station and have it find the right tokens.
Exactly. This would bridge natural language understanding and spatial reasoning. It might involve integrating BPURF with those large language models that understand spatial concepts. It could lead to research on cross-modal embedding spaces and attention mechanisms that can align language with spatial tokens and relationships.
The potential for more intuitive urban analysis tools is huge. Analysts, even everyday people, could just describe an area and get instant insights. to democratize access to powerful urban analytics.
Another exciting direction is applying BPURF to understand how urban regions evolve over time.
How would that work? Could you treat temporal snapshots of the city as layers in the graph?
That's a great thought. With temporal data, could boundary prompting be used to track how regions change? Imagine analyzing the growing tech corridor over a decade, seeing how its size and entities change.
You probably need to extend BPURF to handle time. Maybe develop new message passing mechanisms that work across both space and time, allowing it to learn urban dynamics.
This research could give us valuable insights into long-term urban development, helping us understand how regions emerge, grow, and maybe decline. It could have a big impact on urban planning and policy, helping us anticipate and shape the future of our cities.
So, to wrap things up, this BPRF paper is a big leap forward in how we can represent urban regions with machine learning. It moves beyond those limitations of fixed boundaries, using this idea of boundary prompting and a rich vocabulary of spatial tokens to create a much more flexible and potentially more accurate way to analyze our cities.
The potential for more adaptable and realistic urban analysis is really exciting. If you're interested in the cutting edge of machine learning research, we highly recommend checking out the paper. You can find the link in the show notes or episode description.
It really gets you thinking about how machine learning can not only help us understand our cities, but also shape their future. Thanks for joining us for this deep dive into BPURF. We'll be back soon with another look at the world of machine learning research.